So let me look up that part. So this is the last part of the molecular physics module. This is about something called the vibrational rotational spectrum. Basically, it is an infrared range experiment. That is to say, everything has to do with transition between the ground state vibrational level, n equals 0 oscillator state, to n equals 1 oscillator state. For the reason that this gap is typically higher than KT, the room temperature thermal energy, such that ordinary temperature, the molecules do not occupy the excited n equals 1 levels. Second point, last time we introduced that in order to fully, completely address the energy of a molecule, we need to talk about the minimum value here, which is the electronic part, which vibrational level is the molecule in, so the n, and then which rotational level the molecule is in, so the L. So we need n and L to specify where the molecule really is. Okay, for example, this one will be n equals 1, L equals 4. And then this one will be n equals 0, L equals 3. All right. We also discussed the selection rules. So delta L being plus minus 1, and then delta N being plus minus 1. Now consider what happens if you have high resolution in infrared experiments. So basically, you are shining in light, something of this h nu, I mean this quanta of photon. So it is possible to have a transition from L equals n equals 0, L equals 1. So the molecule is here, and then according to the selection rules, it could go to n equals 1. Then there are choices. Either it can go to L equals 0. Now, delta N is okay. Delta L is also okay. I will answer the question later. And then it can also go to N equals 1, L equals 2. All right. What is the question? Let me see. What can we do if we know the quantum origin? You cannot do anything quantum mechanically, but now you understand what is the problem. And then I think for an educated leader of the future, this is the basic science that one needs, okay? Then you may be better informed to make decisions on whether you ban CO2 emission or you encourage innovation in the area of capturing carbon dioxide and store the emitted carbon dioxide underground so that you will not emit it to greenhouse, to the atmosphere to become greenhouse gas. Okay, so I think that is a part of the ongoing research. I think at least you now understand why people still is considered alternative like capture and storage. Okay, in addition to banning CO2 emission, things like that. Okay, and then I think in 2050 there is a plan about so-called carbon neutral. So what you emit, the net thing will be 0, things like that. Okay, so that is already a big plan ongoing. Okay, so let me come back to here. Okay, so now we are considering vibrational rotational. Okay, so that means we have to consider a change in N and a change in L that goes with the selection rules. So this is the example that I just made. So you start from here, N equals 0, L equals 2. You have two choices. You can go up in the vibrational level, but then you have a choice on L. You can go to L equals 1, go to L equals 3, okay? So you see, even starting from here, there will be two separated lines. One is lower in energy, one is higher in energy in terms of absorbing the infrared photon, okay? So it is easy to use the formula to work out. So you have delta N being plus minus 1, you have delta L being plus minus 1, okay? Now, if you go up, meaning you start from N going up in N, but L could have two choices, okay? Then you can work out what are the allowed energies in absorbing the photon. What are the specific energies in absorbing that infrared photon? You can easily find that it is h bar omega plus something and h bar omega minus something. Now, that is one punchline. There is nothing that will happen at h bar omega. That is to say, nothing happened like this here, okay? Because you only have delta N equals plus 1, that's okay, but this delta L being 0 is not okay, all right? So that's why you don't have that, and either do you have L equals 2 all the way to L equals 2. That will be another h bar omega situation, all right? So here, notice that it is h bar omega plus something, h bar omega minus something, okay? Putting the two answers together, you see that it is h bar omega with something, all right? Now, what does it mean in the spectrum? So here, I would like you to take note of this very typical and rather pretty so-called vibrational rotational spectrum. Now let's analyze it. First of all, look at the frequency. Now it is at 10 to the 13 power hertz. So 10 to the 14 to 10 to the 15 is what our eyes can see visible. So it is lower than what we can see. So it is infrared, okay? Now, infrared, then you come to your mind that it must be related to vibration. Yes, that has to do with delta N transition, so vibrational spectrum. Secondly, look at the labels. The labels are very close to each other. So this is 8.4, this is 8.6. So this much is only 0.2 times 10 to the 13 hertz, or 2 times 10 to the 12 hertz on the scale that is 10 to the 13 hertz. So all this means it is high resolution spectrum, okay? We are seeing details in the mark of 0.2 times 10 to the 13 hertz on a scale of 10 to the 13 hertz, okay? So that is high resolution. That's why we see these details. Think about a low resolution experiment. You have a ruler and in inches, and you cannot see 0.1 millimeter, right? So all you can see is there is something there, okay? So nothing, something there. Now what we are doing is that we put our eyes onto that something and then blow it up, and then you see that these details. Okay, so that is the vibrational rotational spectrum. And now indeed, you see something like a missing line. This, well, you follow the pattern, you would expect there is something here. So there is a gap here, okay? And now we understand this gap, you can read it out and it is h bar omega, all right? And then on the two sides, they refer to lines that come from the lower one, you have a delta L being +1, and then on the other side, you have delta L being -1. So from h bar omega, slightly higher in energy and slightly lower in energy. So that is the reason for this rather pretty spectrum. So, well, there are other details. You may think there are two peaks here. Indeed, because there are two isotopes for chlorine, very common. I think it's 25%, 75% in ratio. So when you have HCl, there are, to be very precise, like two different kinds of HCl corresponding to different isotopes. But this is not our focus. Okay, so now we have something to work on. Read this thing out. We know omega, and omega is related to the spring constant, right? Omega is K over reduced mass square root, what you learn in classical mechanics. Okay, two ball with a spring. And if we read out this equal space between adjacent peaks, then we know this thing, okay? Thereby, we can extract the moment of inertia, and the moment of inertia is mu separation square. Therefore, it is possible to solve or to extract the equilibrium separation, which is the bond length. So let me summarize. If you see a vibrational rotational spectrum, wonderful. You read this, you get the spring constant. You read out the average spacing, the spacing between adjacent lines. Okay, this one, okay? Then you get the moment of inertia, thereby you get the equilibrium separation, the bond length. That is the application. So that's all the ideas in this section. Okay, so this is a absorption spectrum. So this is a transmission spectrum, plotting out the missing intensity. Okay, missing means absorbed by the H. This is hydrogen bromide similarly. Okay, so it is absorbed by HBr. And here this label under every line correspond to the delta L. So go from L equals 0 to L equals 1 up there, 1 to 2, 2 to 3, and so on. And then this one goes from L equals 1 to the higher one, L equals 0. So that's why you have the H bar omega missing here. Okay, so this is the typical spectrum. And this is illustrating why you have something on the right-hand side and why do you have something on the left-hand side, being the delta L go to the higher one. So you get 0 to 1, 1 to 2, things like that. And another one being 1 to 0, 2 to 1, etc. Okay. Now, technically, there are names for this right-hand side and left-hand side branch of the H bar omega. It is called R branch and pre-branch, but they don't mean anything, just labeling them. So this is the spectrum. So I copy it through, and now I illustrate the typical procedure to read data out and make use of them to extract useful information. The first thing is to estimate where is the line that should be there but missing. So you can just eyeball test, right? So here, maybe somewhere here, read it out, down here, something like that. So roughly estimate maybe 0.317 dB, okay? And then we recall, what is this number? This is h bar omega, and omega is given by the spring constant divided by the reduced mass. From classical mechanics, you have two bodies with a mass, so the reduced mass is given by this formula. If you don't have time or you don't have sufficient data, when you see hydrogen, that's good, because that is the lightest thing. When you have the lightest thing, 1 over the smaller mass will dominate this sum. So you may approximate it like that, okay? But usually you can look up data easily. Nowadays, you just Google what is the, this is the whole atom's mass, okay? So it will give you something not as integer. You may see something like 1.0017 U, something called atomic unit, atomic mass unit, and then 1 U is something kilogram, 10 to the minus 27 kilogram. Okay, so you can look it up easily, but once you have the number, easy. So you plug number in, you get the exact, more accurate mu. Otherwise, when you see a light one with a heavier one, the light one wins in this reduced mass formula. And then with that, you read out h bar omega, and then you know the reduced mass, you can calculate the spring constant. Okay, so with that, you can calculate something out. But usually, spring constant is presented in another typical unit. So you may need to convert units sometimes. The second thing to do is to try to read out the spacing. So what is this? And then what is that? And what is that? Okay. Typically, one may read out the separation between 4 or 5 peaks, well, or spikes, and then you divide it. So that will be an average separation. The average separation, I just estimated to be, now, this scale, okay, from here to there is 0.01. So it must be much less than 0.01, okay? So this is 0.002 eV. That's my estimation, I just read it out. And then that is again the point that I want to stress. This is the rotational energy scale embedded within the scale of 0.3 eV. That is the high resolution that we are talking about, okay? The whole thing is about 0.3 eV. But we are trying to read out something that is 0.00 something eV. And with this, we know what it is. This number is h bar squared over moment of inertia. Therefore, you can extract the moment of inertia by plugging in the number in the denominator. Okay? So, you know this. Our goal is to get the equilibrium separation, the bond length, easy. You already have the reduced mass, therefore you plug in numbers. The number turns out to be very reasonable. It's 1.4 angstrom. So we know that the wave function decays about this kind of angstrom scale. And if you find a bond length is of this order, at least things make sense. You haven't made any serious mistake, that is to say, okay? So this is an example illustrating how to read out useful information. The rest, now that we are done about the content here, okay? So at this point, basically, we are done with the whole molecular physics module. I just summarized what we did. So we have this molecular spectrum part. We have vibrational energy, typically in the infrared. And then thermal energy usually is not sufficient to populate molecules here. So most molecules will populate in this part, n equals 0, but several rotational levels. So typically, the population is right here. Thereby, we have this rotational vibrational state. And then with excitation, with incident infrared, it can go to the other family, the other series. Then we discuss selection rules, delta N and delta L. And then rotational spectrum, usually in the microwave and touching the far infrared range. This is 10 to the 11 to 10 to the 12 hertz, that range. We just talked about 10 to the 13. That is another 100 times higher. And with this selection rule, we expect very nice equally spaced line in the rotational spectrum in the microwave, from which we can read out the bond length. We just discussed vibrational rotational spectrum. Very nice thing, so a very beautiful thing. And then I think this is carbon dioxide, I think. Yeah, I think so. So I just want to give you more examples so that you see that this form is not very specific to a particular molecules, but rather general for diatomic molecules. It will be more complicated for polyatomic molecules. And the application is to read out things and you get useful information. How strong is the bond? What is the separation, the length of a bond, okay? We also discussed some real life situation, why something is greenhouse gas. And this molecular spectroscopy branch of physics and chemistry were awarded some Nobel Prizes actually over the years. So I list some of them here. Herzberg, a rather famous atomic physicist, he wrote many books, the physics, atomic spectrum, molecular spectrum, one title, a thick book on each one. And then in the late 60s, laser was popular, and then many people use the new laser and then make spectroscopy much more accurate, a higher resolution. And then there is a branch of spectroscopy that I haven't discussed here. It is more specific about in chemistry. It's called Raman spectrum. Basically, in one sentence, we emphasize that some molecules is infrared inactive, meaning they don't have a changing electric dipole moment when they vibrate. And therefore, what we discuss here will not give us any signal, okay? So we don't have any handle to study this kind of molecules? Not quite. There is another technique called Raman spectroscopy that could plot those molecules. So that is a separate idea. And even very recently, 2014, a Nobel Chemistry Prize was awarded to something called single molecule spectroscopy, meaning nowadays the resolution can look into a single molecule even in a cell. So that is why this Nobel Prize was awarded. And I think in general, light matter interaction, this technique or spectroscopy is a very important technique in studying anything, atoms, molecules, solids, materials. So functional materials, even in biology, astrophysics, studying the painting 500 years ago, what is behind what you see. Maybe underneath there is another painting in there. You usually has to use spectroscopy. So it is good to know something about spectroscopy. And I give you a few more specific books on atomic and molecular spectroscopy for those of you who may want to know more. Well, in our department, we have an expert in atomic and molecular physics. So if you want to learn more, go to Professor Wang Dajun. A very final remark, we have been discussing transitions within this lower binding curve due to the electron. There may be higher binding curve, just like the electronic excited states. So for that, usually there's no selection rule, everything can go, but that happens in another range of the spectrum. It's ultraviolet usually. So you will see something like this in the ultraviolet. And then for those who want to learn more about atoms and molecules, in addition to more formal quantum mechanics, I list a few quite nice books here. Okay, the first two, the first one is easy. It's more qualitative. Okay, but all the phenomena are there. And then the second one is very serious. It's a physics book. Okay, I know physics student is a very special kind. Whenever the word chemistry come up, they tend not to like it. But actually, it has to do with a lot of quantum mechanics. So this Blanson, and I don't know how to pronounce the second one, Physics of Atoms and Molecules. It is something like 700 pages that takes you from the beginning of quantum mechanics all the way to beginning postgraduate level atoms and molecular physics. Rather serious stuff. And if you want a nice and easy to follow quantum mechanics book in which atoms and molecules are discussed, starting from knowing nothing about quantum mechanics, this is a very nicely written book. The author really knows how to write, okay? And then another book on chemistry here. So there are some questions, let me see. The last one is, why is this selection rule for atomic transitions but none in molecules? I don't have an easy answer for you, but the fact is that there's none. Now, simple reason. I have tried to hide something not so technical. Now, basically, in a molecule, this electronic graph, I'm answering the last question first, okay? So the electronic curve, even they have this binding train, you have two curves, they don't happen at this, the minimum do not happen at the same place. Okay? So the wave function in the lower curve, will be around the minimum here, but those wave function in the higher curve will be around another minimum. The overlap can be anything. So that is the idea. All right? But let me back it up. Usually, we don't do experiments in that range. Okay? Usually the fingerprint has to do with vibrational rotational spectrum. Okay? Okay, good. There is an earlier question. What is that? The mountain shape. I know what you asked. I answered it in private at the end of the lecture last time. So let me find a spectrum. So are you talking about this? Lee. Okay. Okay. So the idea is as follows. So you may be thinking about what happened here, right? This envelope, okay? Are you doing thermal and statistical physics? Good. So here, it is related to how the molecules populate the rotational level. So the molecules are populating here, okay? And then they will go up to the higher branch. Following me? Okay. Now, do you remember that even for one L, for one value of L, actually there are 2L plus 1 states. For the reason that there is a M, Y, L, M, theta, phi are the solutions. So you have an M there. Okay, do you follow me? Okay, so therefore, if you know thermal statistical physics, for one state of an L, you would expect the population is something like the energy which is L times L plus 1 h bar square over 2I divided by KT. Right? That is for one state. But now for a given L, actually you have 2L plus 1 in front. Because you have 2L plus 1 state hidden under L. Okay, do you follow me? Okay, so now you see two factors. The first factor increases with L. The second factor drops with L. Okay, so I'm putting these two things against L. Therefore, you will have something like that as a function of L. That is how the molecule will populate. Do you follow? Okay, therefore, down there, the molecules populate in this way. When they absorb the photon go up there, it reflects this shape. You follow the story? Okay, so I'm done. Okay, so that is the end of the part that will be the end of the coverage in the final exam. Okay, so up to that last page with references called Molecular Physics 2, that is the end. All right, understand? Okay, any further question? Now, let me see. I want to stop recording once here so that will be one topic. So let me stop recording and then start recording again, okay? Is it the partition function? Yes, it is related to the partition function. It is one term in the partition function. In the partition function, you need to sum over L. Choi, you understand me? Okay. What is it? For the same number of transitions, the high frequency should have higher intensity. Why is that? The intensity has to do with how many molecules you have here, so that, well, if you have more molecules here, the light will be better or strongly absorbed because each one will absorb and then go up. Each photon has, but each photon is being absorbed and go up there. So that is the energy selection criteria. Okay? Now, when you do time-dependent perturbation, there is a selection in the energy. Do you remember there's some complicated sine square, something over something, the big function with that peaks? So that will select the right photon for absorption. That is giving us these lines. Okay. All right, so now I would like to stop recording so that we have a cutoff on the molecular physics part, okay? And then I will continue on and start the very last part, which is optional for the exam purpose. It is about tunneling, okay? So let me stop recording.